So we've got, for this function, we got to figure out what we would think would be like the outside equation and what would be the inside. So on the outside of this, what is the function or what is the operation that we are doing? Yeah, so it's that to the 1/2 power, right? So it's like we got something in here and it's being raised to the 1/2 power. So that like outside box is that something being raised to the 1/2 power. The inside function on this is the 2x minus 3. Okay, so if we're taking the derivative, this is what it's going to look like. First of all, make sure you label it f prime of x. Notice I called this f of x because I was not taking the derivative. I was just rewriting it so it would be a little bit easier to see how to take the derivative. So this red box on the inside, I'm not doing anything with it. I'm treating it like it's just an x right now. So it stays the same. I will have 1/2. I will multiply out front. Inside stays the same, 2x minus 3. And then I will subtract 1 from 1/2 and I'll get negative 1/2. Okay, so that was the derivative of the outside of the green box, of the something to the 1/2 power. But I must multiply this by the derivative of the inside function. What is the derivative of 2x minus 3? 2. So I must multiply this by 2. And so everything here is multiplied. I would do this 1/2 times 2. What's that going to give you? 1. So that kind of they kind of cancel each other out right there, right? So really, this is just 2x minus 3 to the negative 1/2. You can stop there if it's free response. Most of the time, they're going to send that back down to the bottom. 2x minus 3 to the 1/2. And a lot of times, they'll change it back to a root. 1/2 square root of 2x minus 3. Like that. And so this would be your derivative. Mm-hmm. The like Russian nesting dolls, is that what they're called? Where you got like the dolls that are inside of, yeah. Or the Russian one's eggs. Doll. There's definitely dolls. Are there eggs too? There's eggs too. Yeah. Oh yeah. I think I'm combining two things. Yeah. All right. So yeah, it's like those, or there's all kinds of things you could think about. But you got to do the outside before you can get to the inside for that. Okay, now, example 3 does not have to be done with chain rule. But I'm teaching you chain rule. So, actually 3 and 4, neither one of them have to be done with chain rule. But I'm teaching you chain rule, so I'm going to show you how to do these problems with chain rule. So, for example 3, it could be done with quotient rule. It's not that difficult to do it with quotient rule. I just want to give you another option. In fact, now that we know chain rule, it is possible that you could never do quotient rule ever again if you don't like it.
You have me sold.
Now, because right now this is something over x plus 1 to the first power. I can write this as x plus 1 to the negative 1 power. Okay? Now, I'm not necessarily saying this is easier. I'm just giving you another option, right? So, if I want to take the derivative of this using chain rule instead of using quotient rule, I'd have to make it negative exponents first. And then I would do the outside is that to the negative 1 power. The inside is the x plus 1. So I would have negative 1 times x plus 1 to the negative 2 power times the derivative of the inside, which is just 1. I'm going to write it so you guys know I didn't forget to take it, but you don't have to really write it. If I simplify this, I just have that negative 1. they would probably send the x plus 1 back down to the bottom and give it a positive exponent. For whatever reason, possibly my aversion to memorizing formulas, I don't like memorizing formulas. I think pretty much all through high school, I did not use quotient rule, and I just did this every time. There are some times now as a teacher, like quotient rule is a little bit easier on some problems, so I would not throw quotient rule away. But if you like, I like to streamline like my processes, so if I could get rid of one rule, I think that's what I was doing. It's like, I don't need to ever do quotient rule again. I'm just going to use negative exponents on everything. All right. Now, example 4. Okay. So, I can do example 4. Larry, put that computer away. We do not need it right now. All right. I can do example 4 without chain rule. But to do example 4 without chain rule, it's even worse than the warm-up, right? I've got to expand 2x minus 5 to the 5th power, which means I either got to use Pascal's triangle or I would have to multiply 2x minus 5 times.
I'd really rather not do that.
The numbers are going to get huge, right, because I've got a 2 and a 5, and they're going to have to be raised to the 5th power. Without a calculator, that's a nightmare. With chain rule, it's really not that bad. And the answer choices on something like this are usually not going to be like the long expanded out answer. It's usually going to be factored out, which means chain rule is going to be much better for this. So our outside is that something being raised to the 5th power. Our inside is the 2x minus 5. So if I'm doing f prime of x, I would have 5 times 2x minus 5 to the 4th power. I would multiply this by the derivative of the inside stuff. What is that going to be? Just 2. Now all of this is multiplied, so that 5 and that 2, I can multiply those together. So I would have 10 times 2x minus 5 to the 4th power. I hope that we can all agree that that would be much easier than doing it the other way. We'll just imagine doing it the other way. We're not going to actually do it because it would take up forever. Yeah, if you took the derivative, you could keep on going. You would eventually get, no you wouldn't. You could keep on going forever. You could take the derivative forever. We're actually going to look at, in this unit, doing derivative more than once. A second derivative, and a third derivative, and a fourth derivative. Tangent line of a tangent line.
Well, but isn't it all the same thing?
Yeah, the rules would be the same.
Well, like if you take that derivative of that again, it's truly the same value, though, right?
Mm-mm.
Get the same, like,
you would get 40 times 2x minus 5 to the 3rd power times 2.
Yeah, but like,
and it'll give you different values.
Well, like I mean, like if you expanded it, like if you took the derivative, expanded that, and expanded that, and expanded that, it all come out to the same thing.
Well, it depends what point.
Yeah.
Isn't it? Like,
well, we're going to look at graphs of them more, but like the derivative of something to the 5th power is something to the 4th power. So you're looking at the slope of the tangent line of, so this gives you slope of tangent line. What happens, it has a lot of like really good applications because, and we'll look at them eventually, we just got to learn how to do it first. But whenever, like if we have, because your first equation is position or height, then your first derivative is velocity. Your second derivative is acceleration. The third derivative, I don't know enough about science to know exactly what it is. But the third derivative is sometimes called the jerk. I don't even know what that means, like in like picturing like what that means. Yeah. But I know that a lot of times I see math t-shirts that say things like "Don't be a third derivative," because it's called a jerk. So, That's all I know about that. But and we don't cover that in this class. But yeah. All right, let's look at 5. And all my directions are on these. Or find the derivative. I didn't write it out every time, but. All right, so I got y equals 2x minus 3 times tangent of x squared. Now, for this, I need to know outside function and inside function for this. Not really. The outside is not really the whole thing here. Because 2x is separated from this stuff with a minus sign. So when you take the derivative of this, you're just going to take the derivative of 2x, which is 2. Right? So this part of the function does not need a chain rule. It's just a straight power rule. Derivative of 2x is 2. It's only over here on this part that you need a chain rule. So sometimes it's easiest to identify the inside function. What is the inside function here? The x squared. That's your inside. Your outside is this tangent. You could include the minus 3 with it if you want, or not. That 3 is just like a coefficient. So it's just going to kind of be out front, whichever way you do it. Now, if that 3 had an x with it, then it's even more complicated because it is a product rule. It is a product rule with a chain rule inside of it. So we'll get to some of those, but not quite yet. All right, so if we're taking the derivative here, y, we can either call it dy dx or we can call it y prime. I'm going to use those interchangeably. Derivative of 2x is just 2. And so what I'm going to do is I'm going to just treat this 3 like it's a coefficient here and leave it out front. You could group that 3 with the tangent and use that as part of the derivative. It's still just a coefficient, so it doesn't change the way you work it out much. So, what is the derivative of tangent? Secant squared. So it is secant squared of, don't change the inside stuff, secant squared of x squared. But we must also multiply this by the derivative of the inside. And what is the derivative of x squared? 2x. Okay? If it's free response, you can leave it here. Usually they'll clean it up a little bit. So can I do 2 minus 3 is negative 1? No. It feels like you should do 2 minus 3 is negative 1 because there it sits and it looks so easy to do, right? 3 is multiplied by all this other stuff right here. It's not like terms. So that 2 is separate. All of this stuff over here, like this stuff right here, that stuff can be combined because everything's multiplied together there. So you can multiply this 3 times this 2x over here and get 6x secant squared of x squared. And that's about all you can do on that. That will give you the slope of this graph. Now this graph itself is not a straight line because tangent lines, they'll give you the slope at any point. If they asked us to find a tangent line, they would ask us to find a tangent line at a point. And so then we'd plug in whatever that value is. It would give us the slope at that point. So the slope at 2 is not going to be the same as 4 or 7. So it gives you the slope, whenever you plug it in. Okay, questions? All right, now, you can do 6 2 different ways. this can be done as a triple chain rule because you got the cube root on the outside, you got the square on the inside of that, and then you got the x squared minus 1 on the inside of that. So it can be done with a triple chain rule. However, as you can imagine, doing the chain rule inside of the chain rule starts to get a little bit complicated. Is there a way I could rewrite this so I would not have to do a triple chain rule?
Do 1 to the third. 1 to the 1/3. Okay.
So if I've got x squared minus 1 squared to the 1/3 power. Is that what you meant, Luke?
Yeah.
Okay. Now, remind me, if I've got something like x squared to the 3rd power, if I'm raising a power to a power, what do I do with those exponents? I multiply them, it'd be x to the 6th power, right? So that's what I'm doing right here. I'm raising a power to a power. So I can just multiply those together. 2 times 1/3 would give us x squared minus 1 to the 2/3. And so now I have combined those, and I do not have to do a chain rule inside of a chain rule. Does that make sense? Okay, so now that 2/3 power, that's our outside. The x squared minus 1, that's our inside. So when we take our derivative here, and we'll have multiply 2/3 on the outside. Leave the inside the same. Do not change it. Subtract 1 from 2/3. What you going to get? 2/3 minus 1 is going to be 2/3 minus 3/3, which will give you negative 1/3. Sometimes it feels like you're done when you do that, but you're not, because that was just the derivative of the outside. What's the derivative of the inside? 2x. Now, I think whenever you got fractions, sometimes it's helpful to do this, put everything like over 1 so you kind of know what you're dealing with, because sometimes it's hard to tell what goes to the top and what goes to the bottom. I would move that 1/3 back down to the bottom, so I got 2/3 times 1 over x squared minus 1 to the 1/3 times 2x over 1. And then you can multiply all the top stuff together, so you will get 4x on the top. On the bottom, you will get 3. They might leave it like this with the 1/3 power, or they might change it back to a root. I don't like changing it back to a root, because then you got the 3 and the cube root right there next to each other, which looks confusing, but it could be written that way. Yeah. Technically, for free response questions, you can be done right here. Although sometimes it's helpful to simplify it because you might have to use it for something else. But multiple choice, they're usually going to do probably one of these two right here. Okay, questions on those? All right, let's look at 7. You can do 7 a couple of different ways. You can do 7 as a quotient rule, but even if you do 7 as a quotient rule, you still are going to have to do chain rule inside of that, because you've got you have the 3x minus 4 to the 2nd. So that denominator is going to require chain rule no matter how you do it. It's easier, whenever you just have a number in the top, it is easier to move that up to the top and give it a negative exponent before you take the derivative. And we'll look more about using quotient rule with chain rule. Sometimes you do have to do quotient rule with chain rule, but we'll look at that. We're going to work on this for a few days, so we're not going to go that far yet. But if you just have a number on top, you can send it up to the top. Even if you do have an x, you can do this. You'll just have to use product rule. But now, I think this makes it much easier to deal with because you can just do negative 5 times negative 2, which will give you 10. You'll have 3x minus 4 to the negative third power. And then what do we need to multiply by here? 3. And so that would be 30 times 3x minus 4 to the negative 3, which a lot of times they'll send that back down to the denominator, 3x minus 4 to the third power. It's a lot easier to do this one this way than to use quotient rule. Quotient rule is going to require a lot of simplification. All right, questions there? All right. Okay, now 8. We're just going to do, I think we're just going to do one of these today. But we'll get into this more when we do some of the more difficult problems. 8's a little bit different. I am going to rewrite this as x squared times 1 minus x squared to the 1/2 power. Because pretty much anytime you're taking derivatives, roots have to be thought of as fractional exponents. So what is the outside for this one?
X squared over 2.
It is not going to be that way. What? No. This one is a problem that requires more than one rule. You have to use product rule for this because these two things are multiplied. And you have something right here that has an x multiplied by something else over here that also has an x. Okay? So those two things require product rule. But within this green box, you have to use the chain rule because you've got an inside piece right here. So you are doing product rule, which means you need to do f of x, which is just our x squared, times the derivative of g of x. So that's going to be derivative of what's in that green box, which has to use the chain rule. So to take the derivative of this green box right here, we'll do 1/2 times 1 minus x squared to the negative 1/2 times, we got to multiply by the derivative of the red box. What is the derivative of the red box? Negative 2x. Make sure you don't forget that negative. Also, when you write it, make sure you put that multiplication sign, because if not, it's going to look like it's minus 2x, or you can put parentheses around it. Either one is fine. You could do both if you want. Let's go overboard here, so we make sure it doesn't look like it's subtracted. Okay, now, I feel like I'm done. Am I done? That's only the first half of the chain rule. All right, now I need to do 1 minus x squared to the 1/2 times the derivative of f of x, which is 2x. Okay, so let me go back over what we had. We had f of x, right? This is our f. Probably shouldn't call it f because this is called f of x. But, and this was all of this stuff right here, that long, complicated stuff That was our G prime. Right? And then I had my G times F prime. Now, simplifying this sort of stuff is where it can really become difficult, and there's a few ways to approach it. Before I even think about anything else, I need to clean this up a little bit because everything here is multiplied together. I need to try to put together anything that I can combine. So the x squared, the 1/2, and the negative 2x, those can all be put together. So a 1/2 times a negative 2 is just going to give us a negative 1. And then we'll have x squared and another x over here gives us x to the third. So that is combining the x squared, the 1/2, and the negative 2x. And then we would also have the 1 minus x squared to the negative 1/2. And over here for the second part, I would just write my 2x out front. 1 minus x squared to the 1/2. All right, I'm going to show you guys two ways to simplify this. So, let me copy and paste. Let's move this over here. And this over here. Okay, so you would not need to do both of these. You would do one or the other. I'm just going to show you a couple options for how to deal with this. Because there are times when one works better than the other. Or it may just be that one makes more sense to you than the other. Both are mathematically correct and can be done. So one way that you can deal with this is notice that this piece and this piece are the same, right? Both of those have a 1 minus x squared. So one way we can deal with this is to factor out the greatest common factor, sort of, which is going to be 1 minus x squared to the lowest exponent. So I'm going to factor out 1 minus x squared to the negative 1/2. Okay, so if I do that, I have to write 1 minus x squared to the negative 1/2 out front. And then when you're factoring out a greatest common factor, it's like you're dividing each one of these terms by that. Remember when I say greatest common factor, we're thinking like if I had 3x plus 6. Greatest common factor for that's 3. Right? So you don't really think about it, but what you're doing is you're dividing by 3, dividing by 3. 3 divided by 3 is 1. 6 divided by 3 is 2. So that would be 3 times x plus 2. We're doing the same thing here, just way more complicated, right? So if I've got 1 minus x squared to the negative 1/2 and I divide it by 1 minus x squared to the negative 1/2, those two cancel each other out. And I just have a negative x to the third right there. All right there. Yes? The x squared times 1/2 times negative 2x. So all of those pieces there together will give you the negative x to the third. Then over here, these two do not cancel out because that is a positive 1/2 and this is a negative 1/2. So they don't cancel out. But what I can think about doing, I'm going to do this over to the side and I'm going to erase it because it's on the other side, is I can take that negative 1/2 from the denominator, I can move it up to the top, which will make it have a positive exponent. And then if I put those together, I would add my exponents, and I just get 1 minus x squared to the first power. What should happen with this is that you should end up with something to like a whole number power. So this is just going to be 2x times 1 minus x squared to the first power, which I'll have to write. And then we can distribute here. We'll get negative x to the third plus 2x minus 3x to the third. No, minus 2x to the third. What am I doing? Minus 2x to the third. And then if I combine those, I get negative 3x to the third plus 2x. And then probably what you'll see happen is they'll move that back down to the denominator, 1 minus x squared to the 1/2. And they may even change it back to a root. So 2x, I'm going to write it this way, 2x minus 3x to the third over square root of 1 minus x squared. Questions? I'm going to be honest, when I started teaching this, the idea of factoring this out like that took me a while to wrap my head around. So, but it is a strategy that's going to be particularly helpful when we do quotient rules. So, yes? Most of the time. Particularly whenever you are dealing with something that is like something raised to a power right here, most of the time. Sometimes when we get things like trig or natural logs, e's, stuff like that, you may not see it and you can't really simplify it much. But if it's just like polynomial functions, most of the time. All right, let me give you another option for this because it doesn't have to be done this way. You might find this other way easier, although this is a strategy that works well on some other things that we're going to look at. Here's another strategy. So certainly you don't have to do it both ways, but you could send this back down to the bottom and change it to a root, 1 minus x squared, and then write this one as 2x square root of 1 minus x squared. I'm going to make that over 1 right now. And this way it might be a little easier to understand compared to what we've done so far in the past. So if I want to put those together, I got to have common denominators, correct? So to get common denominators, I would have to multiply this fraction by square root of 1 minus x squared on top and bottom. Which would give me negative x to the third plus, when I multiply square root of 1 minus x squared times square root of 1 minus x squared, what do I get? 1 minus x squared, right? Square root of something times square root of something just gives you that something. So we get 2x times 1 minus x squared right there. And this would all be over square root of 1 minus x squared. And now you just basically have to simplify the numerator. So negative x cubed plus 2x minus 2x cubed over square root of 1 minus x squared, which I'm going to write this way, 2x minus 3x to the third over square root of 1 minus x squared. So that's another way to get to that same answer. Yeah, I feel like you guys probably feel better about the one on the right because it's more similar to things we have done in class. The reason I did this one first, number one, is if I'd done that one first, you'd be like, Miss Hyatt, why'd you even try that one? The second reason is because this strategy right here is going to be useful in some of the more complicated cases that we deal with. Because it may not feel like it's possible, but this is not one of the more complicated cases that we deal with. There's more fun to come. But today, this will be the most complicated that we look at. Okay, questions? All right. Couple more little things that we need to look at. So, we already know that the derivative of a natural log function is 1 over x. Or we should. If we don't, we're going to know that now. So, if we have the derivative of something where we don't just have an x, so that I used a u right here. So it could be something like 3x plus 2, or it could be x squared, or it could be 7x minus 4. So you're taking the natural log of something besides just an x. Then your derivative is a chain rule problem. It's going to be 1 over whatever is inside of the parentheses times the derivative of whatever is in that parentheses. This du over dx is a way of saying the derivative of the inside, or sometimes it's just called u prime. I prefer that second notation there. I'm going to give you a second to copy that down. Du over dx, this would be the derivative of u, whatever is that like inside piece. Also, u prime is the same. That's just two different ways of writing the same thing. So, much like the stuff we've already done with natural logs and e's, whenever you take the derivative of a natural log and e, they're really some of the easiest ones to do. We just panic because we're not real comfortable with natural logs and e's. Because the derivative of the natural log of 3x plus 2 is just 1 over 3x plus 2. That's the derivative of the natural log. Then we have to multiply by the derivative of the inside. What's the derivative of the inside? 3. And that 3, it's like 3 over 1, right? So if we want to put this together, we would get 3 over 3x plus 2. Okay, questions on that? Our next example still has a natural log, but it's different. It is the f of x is natural log of x to the 4th power. What is the outside, or what, let me ask, what's the inside function of that?
1 over x.
The derivative of it will be 1 over x. But just like if I want to put a box around something there, what's the inside? It's that natural log of x. And then the outside is something to the 4th power. So in this case, you're taking the derivative of that something to the 4th power first. So your f prime of x is going to be 4 times natural log of x. Don't change anything about the inside. Raised to the 3rd power. So you're doing that 4th power first on this because that's the outside function. And then we multiply by the derivative of the inside. And what is the derivative of natural log of x? 1 over x. And what you will probably see is they will maybe write it like this. 4 natural log of x to the 3rd over x. Because this stuff is, like it's over 1. So you can notice like that first one that we did with natural logs, it did not have a natural log in its answer at all. It's not very obvious that it was a natural log whenever you look at this. But now 10 does have that natural log still in the problem because it was the inside of that. Look at there. All right, and the easiest of them all is exponentials. Because the derivative of an exponential is itself, right? Derivative of e to the x is e to the x. However, if you have something besides an x here, so I used a u to represent anything besides an x. It could be x squared, it could be 9x minus 2, it could be whatever. Then you have to do the chain rule for that. So the exponent is like your inside function for that. I'll give you a second to write that stuff down. It's u prime. Yeah. It's u prime, which means derivative of whatever the u was, whatever the inside was. That's one reason I think they like to use the d. I didn't put the du over dx, but u prime and u to the first are a little hard. Pretty much know that you would not normally write anything to the first power, so if you see a little tick mark behind something, assume it's a prime. So for 11, we got to take the derivative of e to the negative 3x. The outside part is the e to the power. The inside part is whatever you've got as your exponent. So it would look like this. The derivative of e to something is e to that something. So it's just e to the negative 3x. And then we must multiply by the derivative of the inside, which is our exponent in this case. What's the derivative of our exponent? Negative 3. So it would probably be written like this, negative 3e to the negative 3x. There is a chance, since that's a negative exponent, that they may write it like this, negative 3 over e to the 3x. Okay. All right, questions? All right, so we're going to do, this is not what I have on Canvas. Let me see what I got on Canvas. We're going to do some of that. Let's see. Yeah, 7 through 25 odd and 26. All right, so I want you guys to do 7 through 25 odd, and then I do want you to do number 26. Okay. So you got to